Yeah, thanks to Jyotishman and Ravi for organizing this wonderful meeting, having a precise theme on electron transfer and its related consequences and related aspects. So what I'll be doing in another 20 minutes here is to discuss a bit of success story that we have in terms of organizing molecules that can have sustained charge separated states, essentially motivated from the work that has been shown by Ravi in his introductory remarks, that you can have charges transported across DNA. Is known for quite a long time, and seminal works carried out by variety of researchers have come to a point to think that, you know, if you have 3 bases, it can fairly well transport either electron or hole in such a way that it behaves almost like a conductor. If you have, say, close to 10 bases, it behaves like a semiconductor, and if you have anything further on, it behaves almost like an insulator. Since then, people have started working on variety of structures that can have either sustained charge separated states or you know, enhanced fluorescence or singlet fission generating triplets and variety of photoexcited state processes that one can think of. What I will be focusing on today is the strategy to reduce the rate of charge recombination, and these are the 2 examples that I will be discussing, which is essentially a kind of, you know, modification from this particular work that we carry out in our group. So acknowledgements, these are the work that I am presenting carried out by lots of good PhD students and also BSMS students from our institute, and generous support from DST and DBT and also from IISER-Thiruvananthapuram. And these are the major activities that go around in our group, where we make DNA and crystalline organic structures. They have something in common, that you know, you can have the pi surfaces organized in such a way that you can have the chromophoric separation between the 2 units tuned such that you can have the electronic coupling between the 2 precisely controlled in the crystalline organic structure, but not in the DNA structures. So we are slightly moving from the DNA structures that are easier to synthesize, but crystalline organic structures give variety of chromophoric separations and orbital overlaps that allows us to look into the details of what photoexcited state processes that you can get out of different structures that you can get out of these systems. So we synthesize materials, crystallize them, and perform ultrafast spectroscopy in these structures, and do bit of computational analysis in order to explain the spectroscopic observations we have. We do not do a great extent of theory, but instead use, you know, kind of softwares that are available either from Gaussian or Schrodinger in order to understand these charge transport processes. So if you take organic chromophores and shine light on it, it's been for last 4 decades, people know a great lot about the excited state processes. But what is intriguing is when you have one more chromophore put adjacent onto it, depending upon the orbital overlap between the 2 chromophores, you get totally different behavior generated out of it. As I mentioned earlier, it can at times a singlet fission undergoing triplet generation, or it can be triplet annihilation giving singlet. It can be enhanced fluorescence, and at times it can be charge transport that you derive out of it. Now, if 2 is going to give you this much complicated scenario, what will be the situation that you have when you have lots of chromophores organized together in a crystalline structure or a thin film that one can think of? So we try to understand the photoexcited state processes in an aggregated state that looks like this, either in the crystalline form or a thin film where it exists as a polycrystalline material. These are the major activities that goes around in our group, wherein charge transport across DNA is one interest, but there are other topics of interest that we recently developed, which is if you have a pyrene molecule, which is as available from Aldrich, you crystallize the molecule, you get something called herringbone packing, where you will have 90-degree angle between the 2 adjacent pyrene chromophores. And you will see that, if you shine light onto this material, it appears like a blue fluorescent material. But you keep on doing Friedel-Crafts acylation on this molecule, where you get one acylated, bisacylated, 3 derivatives, trisacylated and tetraacylated. You see that you control the orientation between the 2 pyrene units to get a perfect columnar stack between the 2 pyrene units, such that the electronic coupling between the pyrene units is so large that it ends up becoming more of yellowish orange in fluorescence. So you can tune the fluorescence color just by changing the electronic coupling between the 2 pyrene units. And interestingly enough, yet another study that we took up recently is with the perylene diimide chromophore, wherein we put 4 bromo on the core position that twists the molecule, and twisting the molecule makes sure that they are not exactly on top of each other, but instead the orbital overlap between these 2 units is very limited, close to 4 to 10%. That promotes singlet fission instead of having triplet annihilation, which is what you generally see in the case of perylene diimide system. So depending upon what is the overlap between the 2 units, you can have the properties of the chromophore changed in such a way that you see totally a different photoexcited state processes generated out of it. So what we try to realize over time is that it is not in the chromophore, but it is in the arrangement of the chromophore that dictates most of the time the properties that are associated with it. I will be narrating this in greater detail as I go along. So these are the things that we are majorly involved in. So here you see that a seminal work from Fred Lewis and co-workers from Northwestern University, and that got published in Science almost 18 years back, that you have whole transported across the pi stacks. And the example that they have taken here is DNA by itself. So what we thought is that, can we construct these kind of stacks by some other methodologies and then allow the charges to pass through the stacks such that you can have the charges surviving for longer time scales. So the first effort that we took was to create a vesicular structure of the perylene imide chromophore, wherein you can have a donor that donates an electron to the stack. Injecting that electron, it makes sure that it takes a longer route before it recombines to give the neutral state. And that gives sufficiently long lifetime for the charge separated state. And another strategy we thought was, can we have the donor acceptor systems non-parallel when they are in single molecular state, and seed them to crystallize in such a way that you get non-parallel stacks of the donor and the acceptor, wherein you can have excess energy supplied to the donor or the acceptor to have the charge separation, but while recombining you have a barrier because of the non-planarity that you have both in the molecule as well as the stacks. Pardon me? In which context? I mean, can you precisely say in this or this? Here. I mean, why do you say that you will compromise? I mean, they are not tilted, they are exactly on top of each other here. Extended of pi overlap. You don't need 100% overlap for transporting charge. You barely require some overlap. Even if you do not have any sort of overlap, still charges can transport. So I'll come to the precise point in an example that will be shown in the next slide. Yeah. So from the seminal work of Henry Taube, that you can have electron transport between the metallic complexes, it was recognized in 1983 for this bunch of work that he carried out in precisely metal complexes alone. Since then, people have started understanding electron transport in various contexts, and one of the interesting examples here. So you see that there is no stacking between the 2 units, but you can see that symmetry breaking charge separation between 2 porphyrin units allows the electron to jump from the first pair to this particular chromophore. That allows the electron to go to the next one and further to quinone and to the second quinone. Now if you see the first pair, you have a perfect overlap, but in none other cases you see any overlap between those 2 units. And still you have efficient electron transfer from one unit to the other. So you don't literally require electronic coupling to that extent to promote electron transfer in chromophoric systems. Probably you require a perfect overlap for the first charge separation, but once it is created, you can have them hopping even without the stacks there. But I'm not really sure about that. We don't have any sort of example. So we are trying to synthesize a pair that looks like this, and connected to that we have several acceptors. Almost close to this we are making a molecule, and that probably will tell us whether the charge separation is going to be really longer. So what we do is a perylene diimide system, dimeric, and to that you are putting like porphyrin and quinone. So more or less like the same system that we are building upon. Yeah. Yes. Yeah. That creates a barrier for, you mean forward electron transfer, but you can provide excess energy to have the forward electron transfer. It creates barrier for the recombination, which is what exactly you require. We want to avoid recombination, and you can have ultra-fast charge separation because it is a connected system, and also you can have the injection, by providing the excess energy that you can offer to it. But once that has happened, you can clearly see that the stacks allow the charges to propagate. So we thought that, why can't we mimic these kind of systems? And there is a whole lot done in the literature since the publication from Tom Moore and co-workers from Arizona State University. It's a wonderful synthetic marvel that you would see that you have series of chromophores that will do electron transfer and energy transfer in tandem until it reaches to a point where you have quinone radical anion and you have the radical cation somewhere in the chromophoric system here. But although it is very difficult to synthesize these molecules, the final goal they wanted to achieve is a long-lived charge-separated state was not achieved because they are all connected and you do not have these systems propagating the charge to any other dimensions. Since then, many groups started working in this direction wherein they put some bridge of different lengths to figure out whether that will matter the charge recombination rates. Is again a work that is published from Northwestern University by Wesluski and co-workers, somewhat similar to the DNA work that I have shown. Here the wire is oligophenylene that is being used. You can also see the works from Klaus Mullen and co-workers that you make extremely complicated molecule in order to see whether that can have sustained charge-separated species. And it went on for a while wherein people made different architectures. Until recently when Richard Friend and co-workers came up with an idea that you can have sort of self-sorting by mixing the donor and acceptor, where you get domains that look like this and will create heterojunctions, creating effective photovoltaic efficiency. Now this has been modeled by various theory group in order to understand what it takes in order to mix donor and acceptor together to get a real nice efficiency that you can get out of the system. But more interestingly, synthetic challenges extended in various Japanese groups where you can see that a donor and acceptor system are fused together the way that is shown over here, and you can see the micrographs that clearly shows the two different structures that are being made out of p-type and n-type material, and you fuse them together. It has exceptional photo conductivity on-off ratio that you can measure out of it. Since then, people started working on variety of other structures, like you can have cylindrical structures which are called coaxial structures, and also you can have supramolecular polymerization on surface where you have donor acceptor donor systems that can be parallelly put just next to each other. You can also have helical structures that are created out of donor acceptor system, and you can also have a stack of donor and a helical acceptor surrounded by the donor, are the variety of structures that people have made. But what was not experimented in the literature is a non-planar structure, which people believe for a long time that it can have the charges sustaining for longer time once you create that one. Table shows some numbers wherein charge recombination time scales on monomer and the aggregate. you just find that, these numbers are not that bigger once you take the donor acceptor and then, aggregate them. So what we thought is that, this particular structure is missing. So since 2009, we've been making lots of near orthogonal structures that look like this in order to see whether the crystallization will give a structure that will have the non-planar stacks. And these are the initial efforts that we worked on, wherein you have the donor and the acceptors that are near orthogonal to each other because of the steric hydrogen-hydrogen repulsion that you can have between two naphthalene units. We could succeed in getting some interesting features, but not the stacks that we were anticipating. And here you can see that just by modifying this particular group here, the side chain, we can attain a vesicular architecture that will have the stacks of this perlenemide chromophore, wherein you can have the electron transported or the hole transported across the stack. So we wanted to prove this point, so we made this vesicle first, and that is extremely fluorescent. As you can see here, it's 50% quantum yield for this vesicle. And we threw in indole onto this particular vesicle, where indole is an electron donor, and it doesn't perturb the vesicular architecture. Instead, you can see that after evaporation of the solvent, you can have the indole crystallized on top of the vesicle, which means that, indole might be just floating around in the solution, but it gets precipitated onto the surface. And you can see that the fluorescence is quenched. It's a very nice indication of electron transfer possibility there when fluorescence is quenched. We characterized using steady state and time resolved measurement that it is a bimolecular quenching rate constant, which means that you have a vesicle and you have indole, and upon photoexcitation, indole injects an electron onto the vesicle. It was done in solution. Yeah, but we get a similar result in thin film as well, almost same. With this, KQ we cannot measure in thin film. Yeah, it's too difficult to, do that experiment. Yes. So, so here you can see the femtosecond transient absorption measurements that shows that, the perlenemide chromophore by itself shows the singlet excited state. And the moment you throw indole onto it, which is 1:500 equivalence, it's a large concentration of indole, you get an additional new species here, which corresponds to perlenemide radical anion, which means that indole injects an electron onto this chromophoric system. But the lifetime of this perlenemide radical anion is of the order of 6 picoseconds, which is quite, not that longer. It recombines, pretty fast. So what we thought was, why don't you take the vesicle by itself instead of taking the molecule and throw indole onto that and try to inject an electron onto the vesicular system. So as you can see here, you get 3 species out of this particular trace upon singular value decomposition that corresponds to perlenemide singlet, perlenemide radical anion, but you get also a new species that corresponds to pi-pi stacked perlenemide radical anion. That tells you that after the electron is injected from indole to the perlenemide, the electron transfers across the pi stack such that it gets, the longer route before it recombines. And here you can see that the lifetime got extended to nanosecond time scale, and it is about 1000-fold longer in the vesicular state when compared to the just donor accept mixed together. So what we proposed in this particular work is that if you are making a photovoltaic device, all you need to do is that, do not mix donor acceptor just like that, but instead you try to organize one of these, either donor or the acceptor, and throw the other material. It is going to give you a long-lived charge separated state with the same components that you are mixing them together. Yeah. 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 So when you crowd this, when you crowd this environment, all these vesicles are going to be in contact. And that will make sure that the charges are hopping across these spheres. Yeah, it's electron hopping that you will have. Hole will be delocalized, it will be retained in the indole alone. It will not be delocalized as efficient as the electron. So this strategy has that disadvantage that both the charges will not get delocalized as efficiently as each other. So only one will be delocalized. But you can do the same thing that, you make a vesicle of an indole and make sure that, mix together, which is something that we can attempt. We haven't thought about it so far. Now that you are asking, probably we will try to experiment. Pardon me? Catalysis, yes, yeah. Photoredox catalysis is an emerging area with this kind of strategy, but at the moment we are not working in that direction. Yeah. So this particular work appeared as a cover art in Energy and Environment Science, where you can see that this donor and acceptor mixed together, illuminated with light. You can see that charge separation and recombination is almost spontaneous. And you can see when you create a structure like this, it takes a longer time to recombine. Yeah. So we thought that why do you require an additional donor like indole? Why can't we have a donor acceptor system by itself creating a long-lived charge separated state? Perlenemide, if you are aggregating, you often get a lifetime that is little longer than the monomeric lifetime, and that corresponds to the hexameric lifetime when you get the singlet lifetime from the perlenemide. But with the same constituents, we thought that we will create a donor acceptor system, and the strategy that we adopted was to cut this particular bond that will give you a naphthalene and a naphthalenemide diode. So it's a fairly simple chromophore where you can see that this is the smallest possible chromophore that you can think of, which you can experiment using different lasers that are available. So we thought, if we make this particular compound, can it form this kind of architecture where you have naphthalenes on top of each other and naphthalenemides on top of each other. As you can see here, we made about 87 donor acceptor pairs of different donor and acceptor chromophores. 59 of them got crystallized, and only 2 of them gave an architecture that looks like this. So at the moment, it is purely hit and trial that we have attempted this kind of architecture. And on many of the occasions, I get a question, do you have a perfect design strategy in order to get this a priori, so that you just put these fragments and you get this structure? We don't have answer for that, as such, with so much of experience we have in synthesizing the donor acceptor system, but we are working towards that. Yeah. So there is one major remark that is being told, that crystal engineering is fully done and there is nothing remaining to be done. I will take that statement with a pinch of salt. If it is fully done, just give me the strategy how to make this structure. I'll be happy to do, the spectroscopy with it. Yeah. So as you can see here, we went ahead making molecules with naphthalenemide, just bare chromophore, phenyl substituent and naphthyl substituent. Got the crystal structure as we anticipated, donor on top of each other and acceptor on top of each other. And when we distribute this particular material in solution, you get spherical architectures that look like this, and selected area electron diffraction shows that it is crystalline in nature, almost similar to the crystallinity that you have in the crystal structure. Now we went ahead in order to understand the photophysical properties of these molecules. I am not elaborating that due to lack of time now, but I will be happy to discuss this with you if you want more details. But they form a ground state charge transfer complex, and it has been analyzed using Lippert-Mataga plot. You can see that it's a very strong charge transfer complex that you see in the ground state. It is also interesting that if you keep on increasing the concentration of the solution, you see that the redox potential gets affected, which means that this naphthalenemide chromophore gets easily reduced as you increase the concentration, which is in a way really good for the ultra fast charge separation followed by slow recombination that we are looking for. I will skip 1 or 2 slides here and show one particular slide is the structure that we have created from donor on donor, acceptor on acceptor system. This is how it looks like. If you have a monomer of this molecule, all you see in acetonitrile is a double band that corresponds to a T1 pi star transition, which means that you have charge separation followed by charge recombination populating the triplet excited state. While if you aggregate this material, you see totally different bands as compared to this particular one. And if you do SVD analysis, you see that this triplet band is also seen in this particular case, but other than that, you see 3 new bands. One corresponding to naphthalenimide radical anion, which accepts an electron, naphthalene radical cation after donation of an electron from naphthalene, and then you get a dimer radical cation, which also says that the hole is getting delocalized across the naphthalenes, and it's a nice work done by Kochi and co-workers in the early 90s and late 80s, that this particular species is characterized thoroughly. So we took that literature, and we can see that now the charges are hopping across the stacks that we are creating. So this is the Jablonski diagram. So at the moment, can non-parallel stacks of donor and acceptor chromophores evade Onsager charge recombination? Yes, it can. And you can see that, if you take monomer donor acceptor system, 110 femtosecond, charge recombines. But if you are taking the stack, it goes above 1.2 nanoseconds. Here we write approximately 4.5 microsecond because we don't have the tool to measure the full lifetime of this species because it occurs in the IR region, and our nanosecond spectrometer do not have IR detector, but we have from EPR measurements it says that it is close to 4.5 microseconds. It is time resolved EPR that we have here. So the table is revised. You can see that when our system is taken and aggregated, you see that the ratio of the monomer to the aggregate is about 10,000 fold, and all you do is a simple donor acceptor system, put it in chloroform, remove chloroform, you get a long-lived charge separated state generated. While any number that is comparable to this comes with a very difficult processing of the system, meaning you use different kind of vaporization deposition in order to achieve the same. Now this work appeared as Spotlights, Image Challenge, and also front cover in JACS, and got little bit of attention in terms of new architecture that you can see for the non-parallel donor acceptor system. Now, can we design more non-parallel DA systems? Yes and no at the moment. We got one more luck, that here you see another chromophore, which is asanthraline connected to pyrene, which is all carbon system. It forms the same architecture, but in all the other 85 cases, we did not get the structure. You make little modification in the naphthalene system, it just changes altogether to a different architecture. So this particular work is unpublished, but we have interesting results with respect to this. All characterization, I am skipping that, and thanks for the patient listening.
Perspective, just for us, you need long lifetime for other you need interconnected parts also to get a charge goes to the different electrode. So, do you think it's possible in your case
what do you mean by interconnected parts? I did not get you.
Like when you get a donor and electron at the interface, okay, from the charge separation.
Yeah.
So the electron has to go through another electrode and hold another electrode.
Yeah.
So in your case, what you tell, electron may go, but the hole is getting stuck in the system.
Yeah.
So in case of device perspective, it may induce more recombination in this case.
So if I understand your question correct, what you are asking is that, so this particular part is an electron transporter, and the other one is the hole transporter. And we can align this molecule perfectly crystalline in a thin film. And if you are putting one electrode from this side and the other one from this direction, in principle, you should have a nice device created from here. But not from a single molecule, but from stack of these molecules. And we are measuring the conductivity of this material in the single crystal. And we see that the mobilities are comparable not to rubrene, but it is comparable to pentacene, which is quite good, but not as good as rubrene.
So, do you compare the mobility in this single?
Yeah. So, the conductivity and mobility both are comparable to pentacene, but not to rubrene.
And one more question: what is the dimension of the single crystal?
This one we can grow in almost half a millimeter size.
Yeah, can you please little bit elaborate about the method singular value decomposition? What exactly are you doing by SVD method?
I mean, it's essentially a principal component analysis that you have all the wave packets together. You are trying to isolate them, you know, in different identities. So, in principle, this particular information, just if you are taking the time traces of that, often you get confused how many components are present in it. So if you are getting the eigenvectors that are present in it, you can just tell that, you know, it has 4 different components present in it, and they are unique and different.
So here, what is your inputs? I mean, you have to develop a variance covariance matrix.
That's true.
So, I mean, how exactly are you calculating variance and covariance?
As I said, like, you know, I'm not a great theory person, but there is a software called Glotran, which is available to do this one, fairly standardized. There is also a software called Igor, which does the same thing. So you can have this entire set of data put in there, and what you will get are the different eigenvectors that are available.
So your input is basically the 3-dimensional plot.
It's a 3-dimensional plot that you are getting from the...
And finally you get the comprehensible components. Okay, thank you.
Hello, I have a question. So in your case, you just covalently attached donor and acceptor and non-covalently stacked on top of each other. So compared to this case, if I make a stack like this, I attach the acceptors in a covalent method and donors in a covalent fashion and then try to stack each other. Do you think in which case the charge will be more long-lived?
That is true. Yeah, so we have a system where on the DNA backbone, we are putting this donor acceptor system. And we assume that it will be donor on donor, acceptor on acceptor, although DNA will impart its own helicity to the molecule. So that we are not sure what will be the perfect overlap between the donor and the acceptors. But we will see. We have made the molecule and we are trying to look at the ultra-fast processes.
Thank you.
Sure, yeah. No. Yeah. 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 So what it does is the position does not change, the efficiency changes. That's what we have like noticed. Yeah. I'm not clearly sure about that aspect, what you are asking. So we did submit this paper and it came back stating that we have to do more theory into it in order to evaluate the electronic coupling. And we are not good at doing that one. So we are now presenting that as an experimental paper where we observed singlet fission is all that we are reporting. But to answer your question precisely, we see different yields to the triplet, but we see the same position of the triplet state in the absorption. Yeah, so we can do it in both the contexts. We can make the organized sample in solution and then we remove the solvent and see whether the thin film has the same crystallinity as that of the crystal structure. At the moment, in 3 cases that we have studied, we get the same results with the solution as well as the thin film. So we tend to believe that solvent has no role, at least with these 3 systems, but we are not sure about the generalized perspective on that. Yeah. 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 That is true. Yeah. Yeah. That is true. That is true. Yeah, I agree with you. Yeah. But adding another remark onto that is that, it's not as static as we think in the non-parallel structure as well. Because it has been long studied that these kind of twisted structure in the excited state can become parallel. Yeah. Yeah, that is true. Yeah, but I mean, we have no control on like how to see whether this gets parallel or, it remains non-parallel. In the excited state at the moment, we cannot do that. Probably, Raman will, yeah.